So just as we were talking about the T state versus the R state, one of the things that I'd like you to recognize about this difference in the T state and the R state is, and this is very subtle, but look at the curvature, the slight curve on that heme molecule. Here's our iron atom or our iron ion in the center. Compare that to the lack of a curvature in our heme molecule or our porphyrin ring in the R state of their protein. So it's this transition that causes that, well, that sort of, if this is your cross section of the heme ring, that porphyrin ring, O2 binds, it flattens it out. That helps kind of set in motion, knocking down the dominoes that cause our transition to our full R state of our protein. Now, there is also a pH impact on O2 binding. Just as we saw, there's tons and tons of ionic bonds that exist between our different subunits of hemoglobin. What I want you to see here is the pH effect on O2 binding to hemoglobin. We've got a pH of 7.6, 7.4, and 7.2. And remember what I said earlier about low P50 equals high affinity. And a high P50 equals low affinity. Okay, so what we've got, and I would like to go ahead and draw out my P50. So here is one, here is another, and here is another. So what this tells us is we're starting at a pH of 7.6, and let's call our P50 here. I'm going to write them out. P50 equals, let's call that 2.5. Our P50 for 7.4 is 3.5, and our P50 for 7.2 is, let's call that 4.5. So what we're seeing is our P50 increase as what happens. We're seeing our P50 increase from 2.5 when our pH is 7.6 to P50 of 4.5 when our pH is 7.2. So our pH goes down, our P50 goes up, which what that means is that as we get a more acidic environment, our affinity for O2 with hemoglobin is going to go down. So acidity is going to cause our affinity for O2 to, or our more acidic environment is going to cause our affinity for O2 to go down. Okay, so pH effect on O2 binding to hemoglobin can be characterized with this. So actively metabolizing tissue generate a high concentration of hydrogen ions. Now, lowering the pH of the blood near the tissues relative to the lungs is going to be done by carbonic anhydrase. Well, that carbonic anhydrase is going to take in CO2 plus H2O to produce hydrogen ions and carbonic acid. So HB affinity, so hemoglobin affinity for O2 depends on the pH. Hydrogen ions bind to hemoglobin and stabilize that T state. Specifically, residue histidine number 146, which whenever that is protonated is able to form a salt bridge with aspartic acid number 94. That's going to lead to the release of O2 in the tissues. Okay, so the pH difference between the lungs and metabolic tissues increases efficiency of O2 transport. This is known as the Bohr effect. So you can kind of characterize the Bohr effect as the change in the relationship between pH and P50. So what we're looking at then is CO2 is produced by metabolism in tissues and must be exported. 15 to 20% of CO2 is exported in the form of carbamate on the N-termini of hemoglobin protein. So what we have is CO2 right here, which is going to be added to the N-terminal of a hemoglobin protein. So what you have is this is known as carbamation, and you form this carbamino terminal residue. The formation of the carbamate yields a proton right here that can contribute as well to the Bohr effect. So you've got two factors that are going to increase the hydrogen ion concentration, this carbamation as well as carbonic anhydrase. The carbamate forms additional salt bridges, again stabilizing, and my face is concealing, the T state. Okay, so as our hydrogen ion concentration goes up, then we are stabilizing the T state of our enzyme, of our protein. So 2,3-bisphosphoglycerate regulates O2 binding. Now, this is a negative heterotropic regulator of hemoglobin function. So negative heterotropic. So what that means is, let's look at heterotropic and think back to homotropic. O2 is a homotropic regulator of hemoglobin because it's its native ligand, but also because O2 is the native ligand for hemoglobin, it is a homotropic effector. It is also a positive effector because it increases the affinity. 2,3-bisphosphoglycerate is the exact opposite of that. It's going to be an allosteric regulator, but it's a negative allosteric regulator. And it's not the same as the native ligand. So 2,3-bisphosphoglycerate is present at millimolar concentrations in erythrocytes, and it's produced from an intermediate in glycolysis in our glucose metabolism. It's a small negatively charged molecule, 2,3-bis-phospho. We've got two phosphate groups there. And what it is going to do, 2,3-bisphospho. Yeah. So here's a negative charge, but here are our two phosphate groups. The small negatively charged molecule binds to the positively charged central cavity of hemoglobin. And what this is going to do is stabilize that T state. We already talked about the T state versus the R state. The T state has a nice core or a pore in the middle of it, and 2,3-bisphosphoglycerate fits right in there perfectly. Negative charges, it's going to form nice hydrostatic interactions with the positively charged residues that exist in the central cavity of that T state. It's going to stabilize it. 2,3-bisphosphoglycerate binds to that central cavity of hemoglobin. Here is that central cavity. Although it's small, it's still a central cavity. Bisphosphoglycerate fits in there. Compared to the R state, that cavity really is not as present, in which case it's not going to be able to bind. Now, 2,3-bisphosphoglycerate allows for O2 release in the tissues and adaptations to changes in altitude. So don't think about 2,3-bisphosphoglycerate as something that's just, oh, it's bad, it's the worst. It will allow for a release of oxygen kind of when it's needed. So we've got two different scenarios, and I'm losing my cursor there. No, okay, I lost my cursor. Oh, okay. What we've got is our PO2 in the lungs at sea level compared to PO2 in the lungs at 4,500 meters, so at a high altitude. 2,3-bisphosphoglycerate is produced in a higher concentration at high altitudes so that it can reduces our, let me erase that, our P50s, or our hemoglobins, let me erase that too, our HB P50, which causes resulting in a release of O2 in the tissues. So there's kind of a benefit to having a certain amount of bisphosphoglycerate and in the proper time and setting. So 2,3-bisphosphoglycerate is beneficial at high altitudes.